The universe stretches before us, an immense expanse of wonder and mystery. Billions of galaxies, each containing billions of stars, drift through the silent, cold vacuum of space. For countless millennia, humanity has looked upwards, towards the distant celestial bodies, filled with an innate curiosity. We have always sought to understand our place within this grand cosmic tapestry. We have yearned to discover the fundamental rules that govern all existence, from the smallest particles to the largest structures. This quest for knowledge defines a significant part of what it means to be human, driving us to explore, to question, and to learn about the vastness that surrounds us and the intricate workings within it. Sometimes in the grand sweep of history, a single mind emerges with such clarity and insight that it forever alters our collective perception of reality. Such an individual acts like a master key, unlocking doors to new realms of understanding that were previously hidden from view. These moments are exceedingly rare, marking pivotal turning points in our intellectual journey. They require an extraordinary combination of profound intellect, unyielding courage to challenge established norms, and perhaps a touch of rebellious spirit. This person sees the world not just as it appears, but as it truly is, peering beneath the surface of the ordinary to grasp the extraordinary mechanisms at play in the universe. That singular transformative mind in the early 20th century belonged to Albert Einstein. His very name has become synonymous with the word genius, a shorthand for unparalleled intellectual prowess. He transcended the confines of scientific academia to become a global icon, a figure whose image is instantly recognizable across cultures and generations. Even those unfamiliar with the complex details of his theories understand his significance. He represents the pinnacle of human curiosity and the remarkable capacity of our species to unravel the universe's deepest secrets. His thoughtful eyes and famously untamed hair became symbols of a mind constantly at work, pondering the cosmos. The revolution Albert Einstein ignited was not one of minor adjustments or subtle refinements to existing scientific theories. Instead, he orchestrated a fundamental reshaping of our understanding of the cosmos, altering our comprehension of its most basic components. Concepts that had been considered absolute and unshakable for centuries were suddenly called into question and then redefined. His groundbreaking ideas would send ripples of change throughout the scientific community and beyond, profoundly influencing the course of the 20th century. His work continues to define our ongoing quest for knowledge, shaping the very questions we ask about the universe in the 21st century and inspiring new generations to explore. Albert Einstein exists in our collective consciousness as far more than just a historical figure. He has evolved into a true cultural phenomenon. His distinctive face, framed by its halo of white hair, and his gentle, perceptive gaze are known and recognized across the globe. People who may never delve into the intricacies of special relativity or the photoelectric effect can still instantly identify his image. This universal recognition is a powerful testament to the profound impact he had, not just on science, but on our shared human culture. He became a symbol of intellectual adventure, a sort of folk hero of the mind, capturing the imagination of millions. Exploring the personality of Albert Einstein reveals a fascinating tapestry of traits. He was the playful rebel, unafraid to question established authority and conventional wisdom, even from a young age. He was the quiet dreamer, often lost in profound thought experiments, visualizing the universe in ways no one had before. He was also a passionate and outspoken advocate for peace, for human rights, and for international cooperation, using his global platform to speak out against injustice. He was not a simple one-dimensional caricature of a reclusive scientist. Rather, he was a deeply complex and multifaceted human being whose life story is made all the more compelling by these rich, sometimes contradictory layers. Beyond the readily identifiable iconic image, there resided a profound and relentless intellectual depth. A burning curiosity ignited in his youth continued to fuel his explorations throughout his entire life. His mind was a crucible, constantly wrestling with the most fundamental and challenging questions imaginable about the nature of reality. What was the origin of this extraordinary intellectual firepower? What specific experiences and internal qualities shaped his uniquely powerful perspective on the universe and humanity's place within its vastness? These are questions that continue to intrigue historians and scientists alike as we seek to understand the wellsprings of such transformative genius and vision. This documentary, Einstein, the Mind That Shaped the Universe, endeavors to journey beyond the superficial layers of myth and popular caricature. Our aim is to understand the dedicated human being who existed behind the towering legend. We will delve into the specific circumstances of his life, explore the rich intellectual environment that both nurtured and challenged him, and examine the unique personal qualities that enabled him to perceive what so many others before him had missed. By doing so, we hope to illuminate how this one individual managed to so irrevocably change our world, offering a more nuanced and complete portrait of his genius. Before Albert Einstein stepped onto the world stage of physics, our comprehension of the universe was predominantly shaped by the elegant laws laid down by Sir Isaac Newton centuries earlier. In the Newtonian worldview, space was conceptualized as a fixed, absolute, and unchanging stage upon which the events of the cosmos unfolded. Time, similarly, was believed to flow uniformly and consistently for all observers, regardless of their motion or location. Gravity, while its effects were well described, remained a mysterious force, an invisible tether that inexplicably pulled objects towards one another. These principles were not mere hypotheses, they were considered fundamental, unshakable truths, forming the very bedrock of classical physics for over 200 years. Then arrived Albert Einstein, a young and audacious thinker who dared to challenge these deeply entrenched and long-revered notions. With breathtaking intellectual courage, he proposed a radically new vision of reality. He suggested that space and time are not the separate and independent entities we perceive them to be. Instead, he argued, they are intimately interwoven, forming a single, dynamic, four-dimensional continuum known as space-time. Furthermore, he posited that this fabric of space-time is not a rigid, passive backdrop. It is an active participant in cosmic events, capable of warping, stretching, and bending in response to the presence of matter and energy. This was a conceptual revolution of unparalleled magnitude. Einstein further astounded the scientific world by proposing a completely novel understanding of gravity. He asserted that gravity is not a force in the conventional sense, not an invisible pull exerted between objects across empty space. Instead, he explained, gravity is the manifestation of space-time itself, curving and contorting in the presence of mass and energy. Imagine placing a heavy bowling ball onto a stretched rubber sheet. The sheet distorts, creating a dip. Smaller objects, like marbles, rolling nearby, would then curve inwards, not because the bowling ball is pulling them, but because they are following the curvature of the sheet. This elegant analogy helps visualize how massive celestial bodies dictate the motion of others by shaping the very geometry of space-time around them. And perhaps his most universally recognized contribution came in the form of a deceptively simple yet extraordinarily powerful equation, E equals mc squared. This iconic formula revealed an astonishing and previously unimagined equivalence between energy and mass, linked by the square of the speed of light, an immense constant. This profound insight unlocked the secrets behind the immense power source of stars, explaining how they could shine for billions of years. Tragically, it also laid the theoretical groundwork for the development of atomic weapons, demonstrating the immense destructive potential locked within matter. Einstein's ideas didn't just add new chapters to physics, they fundamentally rewrote its entire language, ushering in a new era of understanding. Every great narrative has its origins, and these beginnings are often found in humble, unassuming circumstances, far removed from the eventual grandeur of the story's climax. Albert Einstein's remarkable journey towards becoming a towering figure in science did not commence within the hallowed halls of a grand university laboratory or under the tutelage of renowned mentors. Instead, its earliest seeds were sown in the quiet, keen observations of a deeply curious child, fascinated by the world around him. He was born in the city of Ulm, in Germany, on March 14, 1879, into a world that was itself on the precipice of enormous technological and social transformations, a world ready for new ideas. As a young boy, Albert Einstein was not always perceived as the archetypal model student destined for academic greatness. He was often introspective, frequently lost in his own intricate thoughts and daydreams, posing questions about his surroundings with an insistent intensity that sometimes bewildered his teachers and even his family. A pivotal moment in his early childhood one he would later recall with clarity, was receiving a simple magnetic compass as a gift from his father. The silent, invisible force that unerringly guided the needle captivated his young imagination, igniting a lifelong obsession with unseen forces and the quest to discover the underlying harmonious order of the vast cosmos. This innate, early developing inquisitiveness, this persistent refusal to merely accept established facts at face value without deeper inquiry, would crystallize into a defining characteristic of his entire scientific approach. He consistently prioritized understanding why phenomena occurred and why principles were true, rather than simply committing facts and formulas to memory for examinations. This fiercely independent spirit, this internal drive to question and to reason from first principles, would ultimately lead him down intellectual pathways that others had either overlooked or lacked the courage to tread. It was a mindset perfectly suited for challenging the established paradigms of his time. From these initial, seemingly small sparks of childhood wonder and relentless questioning, an extraordinary mind was being meticulously forged. It was a mind that would, in due course, grapple with the most profound and perplexing mysteries the universe had to offer, and emerge with insights that would reshape humanity's understanding of everything. This documentary will take you on a journey to explore these crucial formative years. We will seek out the early influences, the pivotal moments, and the burgeoning intellectual curiosity that were the true seeds of the unparalleled genius that was destined to bloom so spectacularly and change the world forever. The path towards profound scientific enlightenment and groundbreaking discovery is seldom a smooth, straight, or effortless ascent. Albert Einstein's journey to the pinnacle of scientific achievement was certainly no exception to this rule. His life's work was characterized by breathtaking moments of profound, intuitive insight and brilliant breakthroughs that illuminated the darkest corners of physics. However, it was equally marked by extended periods of intense struggle, frustrating setbacks, initial rejection from the established scientific community, and an unwavering, relentless perseverance in the face of formidable intellectual challenges. His compelling story stands as a powerful testament to the strength of human determination when fueled by an insatiable curiosity. We will embark on a chronological journey alongside him, beginning with his university days at the Swiss Federal Polytechnic in Zurich. There, he sometimes found himself at odds with the conventional teaching methods, preferring to learn through his own independent study and thought experiments. We will then follow him to his unexpected and seemingly modest role as a patent clerk in Bern, Switzerland. It was within the unassuming confines of this office, while examining the technical drawings of inventors, that he would experience his Annus Mirabilis, or miracle year, in 1905. During this single year, he produced a series of revolutionary papers that would irrevocably shake the very foundations of classical physics. The narrative will then meticulously trace his arduous and intellectually demanding development of the general theory of relativity. This was a monumental intellectual feat, a decade-long quest that culminated in a completely new and revolutionary vision of gravity, space, and time. We will witness his subsequent, almost reluctant, rise to international fame and global celebrity status, following the experimental confirmation of his theories. He became an icon, a figure instantly recognized worldwide, and he often used his newfound and far-reaching platform to champion humanitarian causes that were deeply important to his conscience, advocating for peace and social justice. However, Albert Einstein's extraordinary life story also encompasses chapters filled with profound sorrow and considerable adversity. We will explore the ominous rise of Nazism in his native Germany, an event that profoundly impacted him personally and professionally. This dark chapter led to his forced exile from his homeland, a painful separation he would never reverse. We will also examine his complex and deeply conflicted relationship with the subsequent development of atomic energy, a power his own theories had helped to unleash upon the world. Through a compelling blend of dramatic reenactments, precious archival footage, and insightful interviews with leading historians and physicists, we will strive to illuminate both the remarkable triumphs and the poignant tribulations of this truly extraordinary and impactful life. Why is it that Albert Einstein, decades after his passing from this world, continues to exert such a powerful and enduring fascination upon us? His name is far more than a mere footnote in dusty history books or a subject confined to esoteric scientific discussions. Instead, it resonates with a timeless quality, evoking notions of profound genius and boundless curiosity. His monumental discoveries were not simply academic exercises conducted in isolation. They fundamentally and irrevocably altered humanity's relationship with the cosmos, changing how we perceive our universe and our own place within its almost incomprehensible vastness. He gave us a new cosmic address and a new set of rules to understand it. Today, the intricate theories developed by Albert Einstein are not just confined to textbooks or university lecture halls. They are deeply and inextricably woven into the very fabric of our modern technological world. These remarkable insights guide the vast network of satellites that orbit our planet, enabling the precision of our global positioning systems, or GPS, that so many of us rely on daily. His work helps us to comprehend the bizarre and fascinating behavior of enigmatic cosmic objects like black holes, and to understand the ongoing expansion of our universe. Indeed, his intellectual legacy is not a static relic of the past. It is vibrantly alive and actively working all around us, underpinning much of contemporary physics and astronomy. Beyond the elegant equations and the paradigm-shifting theories, Albert Einstein represents something even more profound and universally inspiring: the boundless power of human imagination and the unwavering, relentless pursuit of knowledge for its own sake. He demonstrated to the world that the universe, despite all its bewildering complexity and apparent chaos, is ultimately knowable, accessible to human reason and inquiry. He consistently encouraged us, and continues to encourage us through his legacy, to question relentlessly, to wonder freely, and to dare to dream beyond the often restrictive confines of the immediately visible and the comfortably familiar. He championed the spirit of exploration. This documentary, Einstein, the Mind That Shaped the Universe, extends an open invitation to you, the viewer, to embark on an exploration of this truly remarkable and multifaceted legacy. Our goal is to help you understand not just the groundbreaking science he produced, but also the compassionate, complex, and often conflicted man behind these achievements. We aim to allow you to fully appreciate how one single individual, armed primarily with an insatiable curiosity, a powerful intellect, and an unwavering courage to challenge the status quo, could so profoundly and forever change the way we perceive ourselves and the magnificent universe we inhabit. His extraordinary story remains a beacon of inspiration for all people, for all time. This period of quiet contemplation, however, was not one of passivity. It was a time of intense, albeit unseen mental activity. He was building internal models, asking silent questions, and developing a rich inner landscape where the seeds of his later revolutionary ideas would eventually find fertile ground. His quietude was the stillness of a deep lake, its surface calm, but its depths teeming with unseen currents and forming structures. The world into which Albert Einstein was born was one of rapidly advancing science and technology. The late 19th century saw the consolidation of classical physics, with figures like Maxwell having recently unified electricity and magnetism. Yet, unseen cracks were beginning to appear in this seemingly complete edifice of knowledge. It was a world poised for change, waiting for a mind that could perceive these subtle inconsistencies and dare to propose a new way of seeing. Little did anyone in Ulm suspect that the quiet baby born in their city, the boy slow to speak, would one day utter words and formulate ideas that would fundamentally rewrite humanity's understanding of space, time, and the very fabric of reality.
I didn't immediately display the precocious talents that folklore often attributes to budding geniuses. Instead, I was a child who seemed to process the world at my own pace, contemplating things with a seriousness that, well, belied my tender years.
Yet this apparent slowness in verbal expression might have masked a deeper, more intense internal world. While other children might have readily chattered and engaged, young Albert was often lost in his own thoughts, a silent observer absorbing the myriad details of his environment. This characteristic of profound introspection, of looking inward to ponder and question, would remain with him throughout his entire life, becoming a hallmark of his unique approach to the universe's greatest puzzles. His family, noticing his reserved nature, sometimes wondered about his future.
From my earliest days, I was, well, markedly different. I was a notably quiet infant, and my development of speech was unusually delayed. This tardiness in speaking caused my parents some initial concern, a worry that perhaps something was amiss with their firstborn child.
Albert Einstein's story begins not with a thunderclap of recognized genius, but with the gentle arrival of a seemingly ordinary child. He was born on March 14, 1879, in the quiet city of Ulm, nestled within the German Empire. His parents, Hermann Einstein, a pragmatic but often struggling entrepreneur in the electrochemical business, and Pauline Koch, a woman of strong will and a passion for music, provided a loving, secular Jewish household. The Germany of this era was a nation brimming with industrial might and intellectual ferment, yet it also carried strong currents of militarism and conformity. These broader societal influences would subtly shape the backdrop against which young Albert's unique mind would begin its slow, deliberate unfolding, often in quiet contrast to the bustling world outside his window. Albert recognized that the most profound truths about nature often lie beneath the surface of the obvious. That simple compass, a gift meant to comfort a sick child, opened a door to a universe of questions. A door that Albert Einstein would spend his life walking through, always chasing the why behind the what.
That early fascination with invisible forces became more than just a memory. It became a guiding principle in my life.
This was Albert's first real encounter with the concept of a field, a cornerstone of his later work in physics. The compass needle, quivering with its own purpose, seemed to suggest a universe far more complex and interconnected than everyday experience might show, a universe governed by elegant though hidden principles.
From that moment, I realized I couldn't just accept things as they appeared. I wanted to look deeper, to find out what really made things tick.
This wasn't just a child's idle curiosity. It was the awakening of a scientific mind, one that would always be drawn to the unseen and the fundamental. The compass experience gave Albert a crucial understanding that there are things in this world not immediately apparent to the senses, but still real and influential.
I was filled with awe, and I just had to ask, how does it work? What mysterious field, invisible to the eye, could so reliably guide that small piece of metal?
This encounter with the magnetic compass left a deep and lasting impression on Albert's developing mind. Later in life, he would even describe it as one of the most profound revelations of his early years. The needle's unwavering direction hinted at a hidden order in the universe, a system of invisible forces operating according to precise, discoverable laws.
I remember being utterly mesmerized. The needle inside its brass case always pointed north, no matter how I turned it. There was no string, nothing visible holding it in place, and yet something unseen was clearly at work.
When Albert was about 5 years old, a seemingly small but pivotal event took place. While he was ill in bed, his father Hermann, wanting to cheer him up, brought him a simple pocket compass. Now, for most kids, this would be just a passing curiosity, maybe a toy they'd soon forget. But for young Albert, this little instrument sparked a profound and lasting sense of wonder. The Luitpold Gymnasium perhaps unintentionally helped forge the very rebellious spirit that would eventually lead to scientific revolution. It taught Albert the importance of thinking for himself, a lesson he'd carry with him for the rest of his life.
Looking back, I realized that this sense of not belonging, of being different, made me more willing to challenge accepted ideas later on.
He devoured books on geometry, finding in them a clarity and logical beauty that captivated him. But this mismatch between his inquisitive nature and the rigid school system left him feeling like an outsider, a mind that didn't quite fit the mold.
I wasn't lazy, and I wasn't stupid, even if some teachers thought so. I just focused on what fascinated me, and I learned much more from my own reading than from the classroom.
Albert's attitude often put him at odds with the gymnasium's philosophy, where questioning authority wasn't exactly encouraged. While his grades were generally good, especially in math and science, his overall approach was one of quiet rebellion.
My teachers often saw me as a daydreamer, someone not really engaged. But I just couldn't get excited about repeating things without understanding them. I needed to know why.
For a child like Albert, whose mind thrived on independent thought and curiosity, this environment was deeply stifling. He found little joy in the mechanical recitation of facts and dates, feeling that it suppressed true learning.
The school was strict. Everything was about memorizing facts, following rules, and honestly, it felt almost like being in the military.
Not long after Albert was born, in the year 1880, the Einstein family moved from Ulm to Munich. There, his father and uncle set up an electrical engineering business. It was in Munich that Albert began his formal education at the Luitpold Gymnasium. This brief interlude provided Albert with the freedom to cultivate his genius on his own terms. It was a formative experience, shaping his unconventional approach to problem-solving and reinforcing his belief in the power of independent thought, a lesson that would define his entire career.
Those months in Italy gave me the space to let my mind wander and explore. It was when I really started to become myself.
This period in Italy was crucial, not because of formal instruction, but because of the autonomy it gave him. Albert learned that true education was about actively seeking understanding, not just passively receiving information.
For the first time, I wasn't just memorizing. I was really thinking, grappling with big ideas and forming my own opinions.
Free from the rigid curriculum, Albert threw himself into self-study. He explored the works of physicists like Helmholtz, Hertz, and Maxwell, diving into advanced concepts far beyond what most his age would tackle. He also delved into philosophy, especially Kant, whose ideas about knowledge and reality made a deep impression on him.
Arriving in Italy felt like a huge relief. The culture was so much more relaxed, and I finally had the freedom to learn what truly interested me.
The prospect of enduring more years in that rigid environment, now compounded by loneliness, was too much. Taking matters into his own hands, and with a doctor's note for nervous exhaustion, Albert managed to leave the gymnasium before finishing his diploma. He soon renounced his German citizenship, a bold move for someone his age, showing just how deeply he disliked the authoritarian spirit he saw in German society. He joined his family in Pavia, Italy.
I felt so alone, stuck in a place that already felt suffocating. Now without my family, it just became unbearable.
In 1894, everything changed for Albert Einstein. His father's business in Munich failed, and the family moved to Milan, Italy in search of new opportunities. At first, Albert, then just 15, stayed behind in Munich to finish his schooling at the Luitpold Gymnasium. By the autumn of 1896, having successfully completed his studies at Aarau and passed the Matura, Albert Einstein was finally ready to enroll at the ETH in Zurich, equipped with a clearer vision and a mind sharpened for the challenges ahead.
I even wrote a short essay on the investigation of the state of the ether in a magnetic field. It was my first real attempt to grapple with the mysteries of physics.
He developed his first serious romantic attachment to Marie Winteler, one of Jost's daughters. This period was one of personal and intellectual blossoming, where he could explore his ideas more freely and engage in discussions that challenged and refined his thinking. The year spent in Aarau was instrumental in preparing Einstein not just academically, but also emotionally for the rigors of university life. He gained a deeper appreciation for a more holistic and humane approach to education.
I lived with the Winteler family, who were incredibly supportive and intellectually curious. Their home felt like a place where ideas were welcome.
The school in Aarau fostered a more liberal and encouraging learning environment, where critical thinking and student initiative were valued. At Aarau, Einstein thrived. He found the teaching methods more aligned with his own approach to learning, emphasizing conceptual understanding over rote memorization.
The advice made sense, so I enrolled at the cantonal school in Aarau. It turned out to be a completely different world from the strict environment of the Luitpold Gymnasium in Munich.
While he demonstrated exceptional aptitude in mathematics and physics, showcasing his advanced self-study, his performance in the general subjects was found wanting. Consequently, he did not pass the examination on his first attempt. However, the director of the Polytechnic, impressed by Einstein's remarkable abilities in the scientific sections, offered him some encouraging advice. He suggested that Albert attend a cantonal school in Aarau, Switzerland, for a year to complete his secondary education and prepare more thoroughly for the university entrance requirements.
I was confident in mathematics and physics, and all the hours of self-study seemed to pay off. But well, the general subjects like languages and biology were much harder for me.
Despite his intellectual growth during the Italian interlude, Albert Einstein knew that to pursue a career in science, he really needed a formal university education. His sights were set on the prestigious Swiss Federal Polytechnic Institute in Zurich, renowned for its excellent science and engineering programs. In 1895, at the age of 16, significantly younger than most applicants, he attempted the entrance examination. In October 1896, Albert Einstein officially began his studies in physics and mathematics at the Swiss Federal Polytechnic in Zurich. This institution was a beacon of scientific education in Europe, attracting talented students and boasting a distinguished faculty. For Einstein, it represented the gateway to the world of advanced physics he so eagerly wished to explore.
The curriculum was intense. There were courses in theoretical physics, advanced calculus, laboratory work, even philosophy of science. I was finally able to dive into the subjects that had fascinated me for so long.
However, Einstein's approach to his university education was characteristically unconventional. He was not always the most diligent student in the traditional sense.
Some lectures felt, well, outdated. I wanted to learn about the new ideas, Maxwell's electromagnetic theory, for example, but many professors stuck to the old ways.
Consequently, he frequently skipped classes he deemed unhelpful, preferring instead to study the original works of physics masters like Kirchhoff, Helmholtz, Hertz, Boltzmann, and Lorentz on his own. He trusted his own intuition to guide him towards the knowledge that truly mattered, becoming a connoisseur of scientific thought rather than a passive recipient of prescribed information.
I relied a lot on Marcel Grossmann's notes. He was meticulous and organized, qualities I sometimes lacked. Marcel became a true friend.
Another significant figure from his ETH years was Mileva Maric, a fellow physics student from Serbia and one of the few women studying physics at the time.
Mileva and I spent endless hours discussing physics. Her intellect and passion for science matched my own, and our conversations pushed me to think deeper.
Despite his sometimes cavalier attitude towards formal coursework, Einstein possessed a profound and unwavering focus when it came to the subjects that truly ignited his passion. He had an extraordinary ability to concentrate intensely on complex problems, often losing himself in thought experiments that pushed the boundaries of contemporary understanding. His professors, while sometimes frustrated by his absenteeism or his challenging questions, could not deny his exceptional talent and deep intuitive grasp of physics.
The ETH gave me the foundation I needed, but more importantly, it gave me the freedom to pursue the ideas that mattered most to me.
The ETH provided him with the foundational knowledge and, perhaps more importantly, the intellectual freedom to begin formulating the revolutionary ideas that would soon astonish the scientific world, even if his path through its halls was uniquely his own. The struggle to find his footing in the academic world was a harsh lesson in the realities of professional science, but it did not extinguish the fire of his curiosity. Instead, it perhaps steeled his resolve to pursue his unique vision, even if it meant doing so outside the conventional academic structures.
The struggle to find my place in the academic world was a harsh lesson, but it didn't put out the fire of curiosity inside me. If anything, it made me more determined to follow my own path.
It was a period that tested his resilience and his commitment to his scientific passion, a stark contrast to the intellectual ferment he had hoped for. During this challenging interlude, Einstein persevered with his theoretical investigations, driven by an unshakable inner conviction. He managed to complete his first scientific paper, Conclusions from the Capillarity Phenomena, which was published in the prestigious Annalen der Physik in 1901. While not a revolutionary work, it demonstrated his capacity for rigorous scientific thought and his determination to contribute to the field.
I kept up my private studies in physics, no matter how difficult things got. But, honestly, the lack of security and support made it tough.
This was a challenging time, filled with uncertainty about his future and the gnawing fear that his scientific ambitions might be thwarted. The years immediately following his graduation, from 1900 to 1902, were marked by a precarious existence. He struggled to find stable employment, taking on temporary teaching jobs in various Swiss towns, including Winterthur and Schaffhausen. These positions were often short-lived and did not provide the intellectual stimulation or the resources he needed to pursue his profound scientific questions.
I couldn't help but feel that my independent streak and maybe some faculty members' resentment were working against me.
This perception, fair or not, would have consequences. Upon graduation, Einstein faced a period of considerable difficulty and frustration in his search for an academic position. He aspired to become a university assistant, a common first step towards an academic career, which would allow him to continue his research and pursue a doctorate. However, his applications to various universities were met with repeated rejections. None of his former professors at the ETH offered him an assistantship, a significant slight that deeply disappointed him.
Professor Weber once told me, "You're a very clever boy, Einstein, a very clever boy, but you have one great fault. You do not let yourself be told anything." That stuck with me, even if I didn't agree with him.
In the summer of 1900, Albert Einstein graduated from the ETH Zurich with a diploma in physics and mathematics. While he had successfully completed his studies, his academic record was not as stellar as one might expect from a future titan of science. His independent, sometimes rebellious approach to learning, and his tendency to skip lectures had not always endeared him to his professors. This period demonstrates that profound intellectual breakthroughs do not always require the grand trappings of a university laboratory or the constant oversight of academic mentors. Sometimes, a steady job, a quiet space, and an unrelenting curiosity are the most fertile grounds for genius to flourish.
Looking back, I can say that my time at the patent office was, in its own way, a blessing. The practical work influenced me more than I could have guessed.
The patent office became his unlikely cloister, a place where revolutionary thoughts could germinate. Far from being a soul-crushing bureaucratic dead end, the Swiss patent office became Einstein's worldly monastery, a place where he could earn a living while his true work, the rewriting of physics, continued unabated in the private laboratory of his mind. He later spoke fondly of his time there, acknowledging that the practical work of assessing inventions had been a positive influence.
In the quiet of my Bern apartment, or even during lulls at the office, my mind was free to roam the cosmos. I was grappling with those big, profound questions about space, time, light, and matter that had fascinated me for years.
The routine of the patent office offered a structured, albeit undemanding, work life. It provided a regular income, which alleviated his financial worries, especially as he and Mileva Marek, whom he married in January of 1903, were starting a family. Crucially, the work was often not overly taxing, allowing him ample free time, both during and after office hours, to dedicate to his own passionate pursuit of physics.
Every day, I found myself dissecting practical problems and scrutinizing the interplay of mechanics and electromagnetism. I think this, maybe without me realizing it at first, really sharpened my critical thinking and gave me a concrete grounding for my more abstract explorations, especially about clocks and the nature of time.
The work at the patent office, while not directly related to the frontiers of theoretical physics, was nonetheless engaging for Einstein's analytical mind. He was tasked with evaluating the technical feasibility and originality of inventors' claims. This required him to quickly understand the essence of diverse mechanical and electromagnetic devices, to discern clarity from obscurity in technical descriptions, and to apply fundamental physical principles.
At first, it seemed like just a modest job, examining patent applications for new inventions. But honestly, it turned out to be an unexpected blessing. I finally had the stability and mental space I desperately needed to develop my ideas.
After nearly 2 years of frustrating job searches and temporary teaching positions, a lifeline appeared for Albert Einstein. It came through the timely assistance of his loyal friend from his ETH days, Marcel Grossmann. Grossmann's father had connections and recommended Einstein for a position at the Swiss Federal Office for Intellectual Property, the Patent Office in Bern. In June of 1902, Einstein was appointed as a technical expert, third class. The world was largely unaware that in a modest office in Bern, a young, unassuming examiner of inventions was on the verge of unleashing a series of ideas that would forever change our understanding of the universe. The storm was gathering, quietly but powerfully.
I was piecing together puzzles that had baffled even the leading physicists. I questioned long-held assumptions about space, time, the nature of light, and tried to reconcile Newtonian mechanics with Maxwell's electromagnetism. It wasn't just idle dreaming. It was disciplined, focused work.
He was constantly confronted with practical problems involving time measurement and coordination over distances. These everyday considerations, combined with his deep theoretical reading of physicists like Lorentz and Poincaré, who were grappling with inconsistencies in electromagnetic theory, created a fertile ground for his revolutionary insights. He was uniquely positioned to bridge the gap between practical engineering problems and fundamental physical principles.
My work at the patent office, especially looking at inventions about clock synchronization and electrical signals, actually influenced how I thought about simultaneity and time. It all fed into my later work on special relativity.
These informal gatherings provided a crucial intellectual outlet and a stimulating environment where he could test his nascent ideas on sympathetic and critical ears. The camaraderie and intellectual sparring of the Olympia Academy helped sustain his passion and refine his thinking during a time when he was largely isolated from the mainstream academic community.
Those gatherings with friends, the Olympia Academy, were honestly a lifeline for me. We debated everything: physics, philosophy, literature. It kept my mind sharp and my ideas evolving. especially since I was mostly cut off from the academic world.
This period was one of intense incubation, where the seeds of his miracle year were being carefully nurtured. During these seemingly conventional years, Einstein was not working in a vacuum. He formed a small discussion group in Bern, jokingly called the Olympia Academy, with a few close friends, including Konrad Habicht and Maurice Solovine. They would meet regularly to discuss physics, philosophy, and literature, engaging in lively debates that sharpened Einstein's arguments and broadened his perspectives.
I really learned to compartmentalize. I could switch almost effortlessly between the technical details of patent applications and the deepest, most abstract questions about the nature of reality.
The years Albert Einstein spent at the Swiss Patent Office in Bern, from 1902 until 1909, were outwardly quiet but internally tumultuous with intellectual activity. While diligently performing his duties as a patent examiner, assessing the practicality of newfangled devices, his mind was simultaneously engaged in a far grander project, a fundamental rethinking of the very foundations of physics. As the 19th century drew to its close and the 20th century dawned, the world of physics appeared, to many, remarkably complete and settled. The grand edifice of classical mechanics, meticulously constructed by Sir Isaac Newton over 2 centuries prior, reigned supreme. Newton's laws of motion and universal gravitation seemed to explain everything, from the majestic orbits of planets to the simple fall of an apple. Alongside this mechanical view, James Clerk Maxwell's elegant equations had brilliantly unified the phenomena of electricity, magnetism, and light, describing light as an electromagnetic wave propagating through a hypothetical medium called the luminiferous ether. Many physicists believed that the fundamental laws of nature were largely understood, with only minor details left to be filled in. However, beneath this veneer of serene completeness, subtle but persistent cracks were beginning to appear. A few perplexing experimental results and theoretical inconsistencies stubbornly refused to fit neatly into the established classical framework. One such puzzle was the mystery of blackbody radiation, the way heated objects emit electromagnetic radiation. Classical theories predicted an ultraviolet catastrophe, suggesting that such objects should radiate infinite energy at high frequencies, a prediction clearly contradicted by observation. Another troubling area was the behavior of light itself. The concept of the luminiferous ether, supposedly filling all of space to carry light waves, was proving stubbornly elusive, despite numerous ingenious experiments designed to detect its presence or its effect on light speed. Furthermore, the discovery of radioactivity by Henri Becquerel in 1896 and the subsequent isolation of the electron by J.J. Thomson in 1897 had opened up entirely new, uncharted territories. These phenomena hinted at a complex inner world within the atom, which classical physics was ill-equipped to explain. The very nature of matter and energy was coming under renewed scrutiny. Physicists were beginning to sense that the supposedly complete picture of the universe might be missing some crucial pieces, or that perhaps some of its foundational assumptions were not as unshakable as once believed. The air was thick with anticipation, a feeling that something new was on the horizon, though few could predict its revolutionary nature. This was the fertile, yet unsettled, intellectual landscape into which Albert Einstein was about to unleash his extraordinary insights. He was not working within the mainstream academic institutions, where these debates were most prominent, but from his relatively isolated vantage point at the Bern Patent Office. Yet, his deep engagement with the fundamental physics literature, combined with his unique ability to question foundational assumptions, positioned him perfectly to address these nagging problems. The world of physics, teetering on the edge of a profound transformation, was unknowingly awaiting the contributions of this unassuming patent clerk, who was about to redefine its very core principles. The Annus Mirabilis was not just a personal triumph for Einstein, it was a pivotal moment for all of science, launching physics into a new era and fundamentally altering the course of the 20th century and beyond. The quiet clerk had roared, and the world of science would never be the same.
This extraordinary outpouring of transformative ideas within such a compressed time frame is a testament to Einstein's profound intellectual power, his deep intuition, and his years of intense, focused thought. While the world at large was unaware within the quiet confines of his Bern apartment and the unassuming patent office, one mind was single-handedly redrawing the map of the universe.
The first paper, submitted in March, proposed a revolutionary idea about the nature of light, suggesting it could behave as discrete packets of energy, later called photons, thereby explaining the puzzling photoelectric effect. The second, completed in April and submitted in May, provided a theoretical explanation for Brownian motion, the erratic movement of microscopic particles suspended in a fluid, offering compelling evidence for the existence of atoms and molecules. The third paper, unleashed in June, introduced the radical principles of my special theory of relativity, forever changing our understanding of space, time, and motion. Finally, a fourth paper, a short but profound addendum to my relativity paper submitted in September, presented the iconic equation E equals mc squared, revealing the equivalence of mass and energy.
From the nature of light and the existence of atoms, to the very structure of space and time, Einstein's 1905 contributions fundamentally reshaped humanity's understanding of the physical world. It was an unparalleled burst of intellectual creativity, a torrent of genius flowing from a seemingly unlikely source.
The sheer audacity and scope of these 4 papers, all conceived and written while Einstein was juggling his full-time job and family responsibilities, are difficult to overstate. They were not minor extensions of existing theories or solutions to trivial problems. Instead, they tackled some of the most fundamental and perplexing questions that were then challenging the very foundations of classical physics.
Far from the bustling laboratories and esteemed professorships of established academia, I produced 4 groundbreaking papers, all published in the prestigious German scientific journal Annalen der Physik. Each of these papers on its own would have been sufficient to secure a prominent place for its author in the history of physics. Together, they heralded a revolution.
The year 1905 stands as a landmark in the annals of science, a period of such astonishing creative output from a single individual that it has earned the Latin designation Annus Mirabilis, meaning miracle year or year of wonders. This remarkable distinction belongs to Albert Einstein, then a young 26-year-old patent clerk working in Bern, Switzerland. The stage was set for a young patent clerk to provide a breathtakingly simple, yet profoundly revolutionary explanation.
Physicists were struggling to reconcile these strange experimental facts with their established theories. The puzzle of the photoelectric effect was a prominent cloud on the horizon of classical physics, hinting that a radical new idea was needed to illuminate the true nature of light and its interaction with matter.
These discrepancies presented a significant challenge to the otherwise highly successful Maxwellian wave theory of light. The photoelectric effect was a clear indication that something fundamental about the interaction between light and matter was not being correctly understood.
If the light's frequency was below this critical threshold, even the brightest light imaginable failed to kick out a single electron. Conversely, if the light's frequency was above the threshold, electrons were ejected almost instantaneously, even if the light source was very faint. This immediate emission and the sharp frequency cutoff were impossible to explain using the classical understanding of light as a continuous wave slowly transferring energy.
Furthermore, another puzzling observation was the existence of a threshold frequency. For each specific metal, there was a certain minimum frequency of light below which no electrons would be emitted, no matter how intense the light beam was or how long it was shown on the surface.
A brighter light would cause more electrons to be emitted, but each electron would have the same maximum energy as those emitted by a dimmer light of the same color. Instead, the energy of the ejected electrons was found to depend solely on the frequency or color of the light. Blue light, with its higher frequency, would eject electrons with more energy than red light, which has a lower frequency. This was a significant departure from the wave model's expectations.
However, the experimental results stubbornly contradicted these classical predictions in several crucial ways. Scientists observed that the maximum kinetic energy of the ejected electrons did not depend on the intensity of the light at all.
According to the prevailing classical wave theory of light, the energy of a light wave was related to its intensity, or brightness. So, it was expected that a brighter light, regardless of its color or frequency, should impart more energy to the electrons, causing them to be ejected with greater kinetic energy. It was also expected that even dim light, if shone for long enough, should eventually accumulate enough energy to dislodge electrons.
The first of Albert Einstein's revolutionary papers in 1905 addressed a perplexing experimental observation known as the photoelectric effect. This phenomenon, first noted by Heinrich Hertz in 1887, and later investigated more thoroughly by Philip Leonard, involved the emission of electrons from a metal surface when light, particularly ultraviolet light, was shone upon it. Nevertheless, his explanation of the photoelectric effect was so compelling and precise that it eventually led to the acceptance of the dual wave-particle nature of light, a cornerstone of modern quantum mechanics. For this work on the photoelectric effect, Einstein would be awarded the Nobel Prize in Physics in 1921.
This idea of light behaving as particles was a profound departure from the well-established wave theory of light, which had been victorious for over a century. It seemed to revive aspects of Newton's old corpuscular theory of light, but with a crucial quantum twist. Einstein himself acknowledged the heuristic or speculative nature of his proposal, as it seemed to contradict the vast body of evidence supporting light's wave-like behavior in phenomena like diffraction and interference.
The instantaneous emission of electrons was also clear. The energy transfer from photon to electron was an immediate, all-or-nothing event. A brighter light simply meant more photons striking the surface per second, leading to more electrons being ejected. But the energy of each individual electron still depended only on the energy of the individual photon that hit it.
This elegantly explained why the kinetic energy of the electrons depended on the frequency of the light, not its intensity. Higher frequency photons carried more energy. Einstein's quantum hypothesis also beautifully accounted for the other puzzling features of the photoelectric effect. The existence of a threshold frequency was naturally explained. If the frequency of the light, and thus the energy of each photon, was too low, no single photon would have enough energy to overcome the work function and liberate an electron, regardless of how many photons, how intense the light, struck the surface.
According to Einstein's revolutionary hypothesis, when light interacts with matter, such as in the photoelectric effect, it behaves as if it consists of these individual particles of energy, later to be named photons. When a photon strikes an electron in the metal, it transfers its entire quantum of energy to that electron. If this energy is greater than the energy binding the electron to the metal, the work function, the electron is ejected. The excess energy then manifests as the kinetic energy of the emitted electron.
He proposed a truly radical idea, that light energy is not continuously distributed as an electromagnetic wave, but rather is concentrated in discrete, indivisible packets or quanta of energy. Each quantum of light, he suggested, has an energy directly proportional to its frequency, related by the equation E equals hf, where h is a fundamental constant known as Planck's constant, which Max Planck had introduced a few years earlier in his work on black body radiation, albeit with a different interpretation.
In his March 1905 paper titled On a Heuristic Point of View, concerning the production and transformation of light, Albert Einstein offered a bold and ingenious solution to the perplexing mystery of the photoelectric effect.
A clear quantitative theoretical framework linking the observable macroscopic motion of the particles to the microscopic world of atoms was needed to solidify the atomic theory. Einstein recognized that Brownian motion could provide a crucial experimental window into the hidden molecular world. He saw that if the atomic kinetic theory of heat, which postulated that heat is the manifestation of the random motion of a substance's constituent molecules, was correct, then the constant random bombardment of larger suspended particles by these agitated fluid molecules should indeed cause the observed erratic movement. The challenge was to develop a precise mathematical theory that could connect the microscopic behavior of these hypothetical molecules to the observable macroscopic dance of the pollen grains, thereby providing quantitative, testable predictions.
The second groundbreaking paper Albert Einstein submitted in his Annus Mirabilis of 1905, titled On the Movement of Small Particles Suspended in Stationary Liquids, required by the molecular kinetic theory of heat, tackled another long-standing puzzle in physics, Brownian motion. This phenomenon, first systematically observed by the Scottish botanist Robert Brown in 1827, refers to the ceaseless, erratic, and seemingly random jiggling motion of microscopic particles, such as pollen grains or dust specks, when suspended in a liquid or gas. Brown himself was unable to explain the cause of this curious dance, ruling out living organisms or currents in the fluid. For decades, the true origin of Brownian motion remained a subject of debate and speculation. While some scientists hypothesized that the observed jittery movement was due to the random collisions of the suspended particles with the even smaller, invisible molecules of the surrounding fluid. This idea was not universally accepted. In the late 19th and early 20th centuries, the very existence of atoms and molecules was still a contentious issue for some influential physicists and chemists. While the atomic hypothesis was gaining traction and proving useful in explaining chemical reactions and the properties of gases, direct, irrefutable proof of their physical reality was still considered lacking by skeptics. The prevailing scientific philosophy of positivism, championed by figures like Ernst Mach, whose critical views on Newtonian mechanics ironically influenced Einstein, argued that scientific theories should only be based on observable phenomena. Since atoms and molecules could not be directly seen, some positivists regarded them as convenient fictions or theoretical constructs rather than real physical entities. Explaining Brownian motion as the result of bombardment by these unseen molecules was, therefore, met with skepticism in some quarters. Einstein's work on Brownian motion was profoundly significant. It not only provided some of the most convincing evidence for the physical reality of atoms and molecules, effectively settling a long-standing debate, but it also powerfully demonstrated the validity and utility of statistical mechanics. It showed how statistical methods could be used to understand phenomena where the behavior of individual microscopic components is too complex to track, but their collective effect produces observable macroscopic results. This paper, alongside his PhD thesis submitted in the same year, which also dealt with determining molecular dimensions, firmly established Einstein as a master of statistical physics, even as his work on relativity was about to reshape our understanding of space and time.
This compelling agreement between Einstein's theory and Perrin's experiments delivered a decisive blow to the remaining skeptics of the atomic theory. The random dance of pollen grains was no longer a mystery. It was a visible manifestation of the ceaseless thermal agitation of invisible molecules.
His theoretical predictions were soon confirmed with remarkable accuracy by the meticulous experimental work of the French physicist Jean Perrin, conducted between 1908 and 1911. Perrin carefully observed the Brownian motion of tiny resin particles suspended in water, measuring their displacements over time. His results closely matched Einstein's formulas, providing consistent values for Avogadro's number from different experimental setups.
His approach was elegant and profound, forging a direct link between the unseen molecular realm and observable macroscopic behavior. Einstein's theory predicted that the mean squared displacement of a Brownian particle, how far on average it travels from its starting point, would be directly proportional to the time elapsed. More importantly, his equations showed how this displacement depended on specific, measurable quantities: the temperature of the fluid, the viscosity of the fluid, the size of the suspended particles, and a fundamental constant known as Avogadro's number, which relates the number of molecules in a mole of a substance. This was a breakthrough because it provided a concrete, testable way to determine Avogadro's number and thus the size of atoms by simply observing Brownian motion.
In his May 1905 paper on Brownian motion, Albert Einstein provided the crucial theoretical framework that transformed this curious phenomenon from a mere scientific oddity into powerful quantitative evidence for the existence of atoms and molecules. He applied the principles of statistical mechanics and the kinetic theory of heat to develop a mathematical description of the random walk undertaken by a suspended particle due to innumerable collisions with the molecules of the surrounding fluid.
His second postulate was even more revolutionary. The speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer. This directly addressed the perplexing experimental results. It meant that whether you are standing still or chasing a beam of light at half its speed or running away from it, you will always measure its speed to be exactly c, approximately 299,792 kilometers per second. These two postulates, seemingly straightforward, would lead to a complete overhaul of our fundamental understanding of space and time, challenging deeply ingrained intuitions about how the universe works.
This meant that the idea of an absolute velocity, or motion relative to a fixed ether, was meaningless.
The first postulate, the principle of relativity, stated that the laws of physics are the same for all observers in uniform motion, not accelerating, that is. This extended Galileo's principle of relativity from mechanics to all physical laws, including those of electromagnetism. There is no privileged absolute state of rest. All inertial reference frames are equivalent.
Einstein, in a stroke of profound genius, decided to abandon the concept of the ether altogether. Instead of trying to force observations to fit the old framework, he started from two simple yet radical postulates.
This was deeply puzzling, as common sense and Newtonian physics would suggest that if you move towards a light wave, its speed relative to you should appear faster, and if you move away, it should appear slower. Maxwell's equations themselves implied that the speed of light in a vacuum was a universal constant, but it was unclear in which reference frame this constancy held true.
However, numerous experiments, most famously the Michelson-Morley experiment of 1887, had failed to detect any evidence of this ether or Earth's motion through it. The speed of light, when measured, always seemed to be the same, regardless of the motion of the source or the observer.
Classical physics assumed the existence of an absolute space and an absolute time, concepts that Newton himself had laid down. It was also widely believed that light waves propagated through a mysterious, all-pervading medium called the luminiferous ether, which was thought to be at absolute rest, providing a fixed reference frame for all motion in the universe.
The third monumental paper Albert Einstein published in June 1905, Zur Elektrodynamik bewegter Körper, or On the Electrodynamics of Moving Bodies, introduced his special theory of relativity. This theory was born out of deep contemplation on inconsistencies that arose when trying to reconcile Newtonian mechanics with Maxwell's theory of electromagnetism, particularly concerning the behavior of light and the concept of motion. Einstein's 1905 paper on special relativity thus replaced Newton's rigid stage with a dynamic, malleable arena where measurements of space and time depend on the relative motion of observers.
Furthermore, special relativity demolished the notion of absolute simultaneity. Events that appear to happen at the same time for one observer may not appear simultaneous for another observer in motion. Whether two spatially separated events occur at the same time depends on the observer's frame of reference. This interconnectedness of space and time led to the concept of a four-dimensional space-time continuum, where space and time are inextricably linked.
Another striking prediction is length contraction. The length of an object moving at a relativistic speed will be measured to be shorter in its direction of motion, compared to its length when measured at rest. This is not a physical deformation of the object, but a consequence of the relativity of space and time. The object itself experiences no change in its own reference frame, but to an observer in a different inertial frame, its length appears contracted. This effect becomes significant only at very high velocities, which is why we don't notice it in everyday life.
One of the most famous consequences is time dilation. Time passes differently for observers who are moving relative to each other. A clock moving at a high speed will be measured to be ticking slower than a clock at rest. This effect is reciprocal. The moving observer would see the stationary observer's clock as running slow. This isn't an illusion or a problem with the clocks. Time itself is relative. The faster you move through space, the slower you move through time. This has actually been experimentally verified with atomic clocks flown on high-speed aircraft.
From his two fundamental postulates, Albert Einstein derived a series of astonishing and counterintuitive consequences that fundamentally reshaped our understanding of space and time. These were not just philosophical speculations, but precise mathematical predictions that shattered the Newtonian concepts of absolute space and absolute time. The comfortable common-sense notions that time flows uniformly for everyone and that lengths are fixed quantities were shown to be mere approximations, valid only at speeds much slower than the speed of light. The universe, according to special relativity, was a far stranger and more flexible place than anyone had previously imagined. While the 1905 paper only laid the initial groundwork, its simple elegance and profound meaning would ensure E equals mc squared became an iconic symbol of scientific genius and the transformative power of theoretical physics, forever associated with Einstein's name.
It provided a new understanding of where the energy in processes like radioactive decay might originate, and it hinted at the possibility of releasing vast stores of energy locked within matter. The implications of E equals mc squared were far-reaching and would take time to be fully appreciated. Initially, it was a theoretical curiosity, a subtle consequence of the principles of relativity. However, it would later become the cornerstone for understanding nuclear physics, explaining the immense energy released in nuclear reactions, such as those that power the sun and other stars, and, more ominously, the devastating power of atomic weapons.
This was a revolutionary concept, as classical physics had treated mass and energy as entirely separate and independently conserved quantities. Einstein's insight revealed that the mass of an object is a measure of its energy content. If an object emits energy, for example in the form of light, its mass must decrease by a corresponding amount, E divided by c squared. Conversely, if an object absorbs energy, its mass must increase. This equivalence shattered the traditional distinction between matter and energy, showing them to be two sides of the same coin.
The equation E equals mc squared states that energy and mass are equivalent and interchangeable forms of the same fundamental physical property. The c in the equation represents the speed of light in a vacuum, an enormous number, approximately 3 times 10 to the 8th meters per second. Squaring this immense speed, c squared, results in an extraordinarily large conversion factor, implying that even a tiny amount of mass is equivalent to, and can be converted into, a tremendous amount of energy, and vice versa.
As if redefining space and time were not enough for 1 year, Albert Einstein published a short but profoundly impactful addendum to his special relativity paper in September 1905. This paper, titled Ist die Tragik eines Körpers von seinem Energieinhalt abhängig, which means, does the inertia of a body depend upon its energy content, contained the genesis of what would become the most famous equation in the world, E equals mc squared. In this concise work, Einstein demonstrated that one of the consequences of his theory of special relativity was a deep and fundamental connection between mass and energy.
Thus, 1905 was not just a miracle year for Albert Einstein, it was a turning point for physics itself. From the modest setting of the Bern-Patten office, a young, unassuming physicist had unleashed a torrent of ideas that fundamentally altered humanity's perception of the universe. He had challenged centuries-old assumptions, solved perplexing mysteries, and opened up entirely new avenues of research. The echoes of his 1905 breakthroughs continue to reverberate through science today, a testament to the enduring power of curiosity, critical thinking, and the courage to imagine a reality beyond the confines of conventional wisdom. The quiet patent clerk had set the world of physics on an exhilarating new course.
The Annus Mirabilis papers laid the essential groundwork for much of 20th century physics and beyond. The concept of light quanta paved the way for the full development of quantum mechanics, which would revolutionize our understanding of the atomic and subatomic world. Special relativity not only changed our understanding of kinematics, but also set the stage for Einstein's next great intellectual endeavor, the development of the general theory of relativity, his theory of gravity, which he would complete a decade later. The equation E equals mc squared unlocked the secrets of nuclear energy, with profound consequences for both peaceful applications and warfare.
However, the explanatory power of Einstein's theories was undeniable. Slowly but surely, as experimental evidence accumulated and theoretical understanding deepened, the significance of the 1905 papers began to resonate more widely. His explanation of the photoelectric effect eventually became a key piece of evidence for the emerging quantum theory. His work on Brownian motion, powerfully confirmed by Jean Perrin's experiments, played a crucial role in silencing the remaining doubters of the atomic hypothesis and validating statistical mechanics. And special relativity, with its radical reformulation of space and time, began to be recognized as a monumental achievement, resolving long-standing paradoxes and providing a new framework for understanding motion and electromagnetism at high velocities.
The 4 papers Albert Einstein published in 1905 did not immediately catapult him to global fame, nor were all their revolutionary implications instantly embraced by the entire physics community. The scientific world, accustomed to more incremental progress, took time to digest the sheer audacity and scope of his proposals. His ideas on light quanta were particularly controversial, as they seemed to contradict the well-established wave nature of light. Even Max Planck, whose own work on quantization had inspired Einstein, was initially skeptical of the idea that light itself was quantized into particles for all its interactions. The patent clerk who had once struggled to find any university position was now a sought-after professor, his reputation growing steadily as the profound implications of his 1905 work became more widely understood and accepted by his peers.
This was followed by a full professorship at the German Charles Ferdinand University in Prague in 1911. and then a prestigious professorship back at his alma mater, the ETH Zurich, in 1912. His ascent in the academic ranks was now swift.
The transition culminated in 1909 when Einstein was appointed Associate Professor of Theoretical Physics at the University of Zurich. He finally resigned from the patent office, the unlikely haven where he had reshaped physics.
Though modest, it was a significant move, marking his official entry into the academic world he had long aspired to join. He continued to work at the patent office for a time, juggling both responsibilities, but his trajectory was now clearly pointed towards a full-time academic career. The world of theoretical physics was beginning to claim one of its most formidable talents.
In 1908, 3 years after his miracle year, Einstein finally received his first academic appointment. He was offered a position as a lecturer, or Privatdozent, at the University of Bern. This was an unpaid position initially, a common stepping stone in the German academic system, allowing him to teach courses while continuing his research.
Slowly, invitations to speak at conferences began to arrive, and correspondence with other leading scientists increased. The gears of academic recognition, though grinding slowly, were beginning to turn in his favor, signaling an end to his intellectual isolation.
Max Planck, one of the most influential figures in German physics and the originator of quantum theory, became an early and crucial advocate for Einstein's ideas, particularly special relativity. Planck's support lent significant credibility to Einstein's work and helped to introduce it to a wider academic audience.
However, the sheer brilliance encapsulated in his 1905 publications could not be ignored indefinitely. Leading physicists began to recognize the young Einstein as a mind of exceptional originality and power.
His life in Bern continued, with the daily routines of the patent office providing a stable, if unexciting, backdrop to his continued theoretical explorations. He remained dedicated to his physics, patiently waiting for the world to catch up.
While his work on Brownian motion and the photoelectric effect began to attract attention relatively quickly, particularly from prominent physicists like Max Planck, special relativity was a more profound conceptual shift that took longer to permeate the established scientific consciousness.
The extraordinary papers of 1905, Einstein's Annus Mirabilis, did not instantly transform him from an unknown patent clerk into a celebrated academic. The scientific community, by its nature, is cautious, and revolutionary ideas often face a period of scrutiny and skepticism before gaining widespread acceptance. The seeds of general relativity were being sown in his mind, born from the desire to unify his own revolutionary ideas about space-time with the ancient mystery of gravitational attraction.
He sought a theory that would not only be consistent with special relativity, but would also explain gravity in a more fundamental way, perhaps revealing its true nature. He understood that such a theory would need to incorporate the principles of relativity, meaning that space and time themselves might play an active role in how gravity operated.
This quest for a new theory of gravity would become Einstein's central preoccupation for the next decade, a period of intense intellectual struggle and profound creative insight.
Newton himself had famously declined to speculate on the cause of gravity. Hypotheses non fingo, I frame no hypotheses, content to describe its effects mathematically. Einstein, however, was driven to understand its underlying mechanism.
How could one modify or replace a theory that had stood as the bedrock of physics for over 200 years and had been confirmed by countless observations and experiments?
This deep inconsistency troubled Einstein immensely. He realized that Newton's elegant and time-tested theory, despite its incredible successes, must be an approximation, a special case of a more fundamental theory of gravity that was consistent with the principles of relativity. The challenge was immense.
According to Newton, if the sun were to suddenly disappear, the Earth would instantaneously fly off its orbit, as the gravitational pull would vanish at that very moment. This instantaneous effect, propagating across vast cosmic distances in no time at all, directly contradicted the finite speed limit imposed by special relativity.
However, Einstein recognized a fundamental incompatibility between Newton's theory of gravity and his own newly formulated special theory of relativity. Special relativity had shown that nothing, not even information, could travel faster than the speed of light. Yet Newton's law of gravity implied an instantaneous action at a distance.
Newton's gravity explained the fall of an apple, the orbits of the planets, and the tides of the oceans with remarkable precision. It was a cornerstone of classical physics, a seemingly immutable law of the cosmos.
Sir Isaac Newton's law of universal gravitation, formulated over 2 centuries earlier, had been astonishingly successful. It described how objects attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them.
Even as Albert Einstein was gaining recognition for his groundbreaking work on special relativity and quantum theory, his restless mind was already grappling with a new, even more profound challenge: the nature of gravity. This insight suggested that gravity could bend light, a prediction that would later provide a crucial test for his emerging theory, and set him on a path to redefine our understanding of the universe's structure.
If gravity and acceleration were equivalent, then light, which would clearly be affected by the acceleration of its source or observer, for example, its path would appear curved in an accelerating rocket ship, must also be affected by gravity.
The principle of equivalence became the cornerstone of Einstein's efforts to develop a relativistic theory of gravity. It provided a powerful conceptual tool for understanding how gravity could affect not just massive objects, but also light, which has no mass in the conventional sense.
This was a radical departure. Newton had viewed gravity as a force pulling objects through a fixed, absolute space. Einstein began to suspect that gravity might not be a force at all, but rather a manifestation of the geometry of space-time itself, influenced by the presence of mass and energy, and experienced as acceleration.
Gravity and acceleration, which seemed like distinct phenomena in Newtonian physics, were, in some fundamental sense, equivalent.
This idea became known as the principle of equivalence. It states that there is no local experiment one can perform to distinguish between being in a uniform gravitational field and being in a uniformly accelerating reference frame.
Similarly, an observer in a closed chamber accelerating upwards in empty space at a certain rate, say 9.8 meters per second squared, the acceleration due to gravity on Earth's surface, would feel a force pressing them to the floor, identical to the force of gravity.
If the man in the falling elevator, a common variation of the thought experiment, were in a closed chamber, he would have no way of knowing whether he was truly weightless in space, far from any gravitational source, or if he was in a gravitational field but accelerating freely within it.
This thought experiment led Einstein to a profound realization. The effects of gravity are locally indistinguishable from the effects of acceleration.
He was pondering the experience of a person in free fall. Imagine, he thought, a man falling from the roof of a house. As this man falls, he would not feel his own weight. If he were to release objects from his pockets, they would remain suspended beside him, seemingly weightless, rather than falling relative to him.
In 1907, while still working at the patent office in Bern and deep in thought about the problem of gravity, Albert Einstein had what he would later describe as the happiest thought of my life. This pivotal insight provided the crucial conceptual breakthrough that would guide him towards his general theory of relativity. The search for general relativity was a testament to his extraordinary perseverance and unwavering belief in his physical insights.
Together, they explored various formulations, trying to find field equations that would correctly describe how mass and energy curve spacetime, and how that curvature, in turn, dictates the motion of objects. There were numerous false starts, moments of despair, and periods of intense frustration. Einstein later described this period as one of immense mental strain, groping in the dark for the correct mathematical structure.
It was here that his old friend from his ETH student days, Marcel Grossmann, now a professor of mathematics, played an invaluable role. Grossmann introduced Einstein to the intricacies of Riemannian geometry and tensor calculus. The collaboration with Grossmann was crucial. While Einstein provided the physical intuition and guiding principles, Grossmann supplied the necessary mathematical expertise.
During his time as a professor in Prague, from 1911 to 1912, and later back at ETH Zurich, from 1912 to 1914, Einstein intensified his efforts. He realized that the mathematics he needed was a branch of differential geometry dealing with tensors, mathematical objects that can describe physical quantities in curved spaces, independent of the coordinate system used. This was a highly specialized field, and Einstein, primarily a physicist, was not initially an expert in these advanced mathematical techniques.
If gravity was indeed a manifestation of curved spacetime, then he needed a mathematical framework capable of describing such curvature and how it changed in the presence of matter and energy. This was uncharted territory.
Initially, Einstein struggled to find the appropriate mathematical language to describe a universe where gravity was not a force, but a feature of space-time geometry. Special relativity dealt with flat, uncurved space-time. However, the equivalence principle suggested that gravity was related to acceleration, and accelerated reference frames implied a departure from the simple, flat geometry of Minkowski space-time used in special relativity.
He knew that his new theory must reduce to Newton's law of gravity in the limit of weak gravitational fields and slow velocities, yet it also had to incorporate the principles of special relativity and the equivalence of gravity and acceleration. The path was far from straightforward.
Armed with the powerful insight of the equivalence principle, Albert Einstein embarked on the arduous journey of translating this conceptual breakthrough into a complete and mathematically rigorous theory of gravity. This quest would consume the better part of a decade, from roughly 1907 to 1915, and would prove to be the most intellectually demanding challenge of his scientific career.
They represented a new vision of the cosmos, one where gravity was woven into the very fabric of reality. General relativity was not just a new theory of gravity, it was a new theory of space-time itself, offering a framework to understand the universe on its grandest scales, from the dynamics of galaxies to the evolution of the cosmos as a whole.
The Einstein field equations are a set of 10 coupled, non-linear partial differential equations, notoriously difficult to solve, except in the simplest of cases. However, their mathematical beauty and profound physical implications were immediately apparent to those who could grasp them.
What we perceive as gravity is simply the effect of objects following the natural pathways, or geodesics, through this curved space-time. A planet orbits a star not because the star is pulling it with an invisible force, but because space-time around the star is curved, and the planet is simply following the straightest possible path in that curved geometry.
This was a radical departure from Newton's concept of gravity as a force acting through a passive, unchanging space. In Einstein's vision, space-time is not merely a static stage upon which cosmic events unfold. It is an active participant, a dynamic entity that can be warped, stretched, and rippled by the presence and motion of mass and energy.
The equations dictate that the presence of mass and energy determines how space-time curves, and conversely, the curvature of space-time determines how matter and energy move through it. John Archibald Wheeler later famously summarized this core idea as, "Space-time tells matter how to move, matter tells space-time how to curve."
In essence, the Einstein field equations describe a dynamic interplay between matter and energy and the fabric of space-time. On one side of the equations is a term representing the distribution of mass and energy in a given region of space-time. On the other side is a term representing the curvature of space-time in that region.
The culmination of this decade-long quest was a set of elegant but formidable equations known as the Einstein field equations. These equations form the very heart of general relativity, providing a complete mathematical description of how gravity works as a manifestation of space-time geometry.
After years of relentless intellectual struggle, marked by breakthroughs, setbacks, and intense collaboration, Albert Einstein finally arrived at the mathematical formulation of his general theory of relativity in November 1915. He presented his findings in a series of lectures to the Prussian Academy of Sciences in Berlin, where he had recently taken up a prestigious research professorship. The completion of general relativity during such a dark chapter in human history stands as a poignant reminder of the enduring quest for knowledge and understanding, a beacon of reason in a world seemingly consumed by irrationality and destruction.
It was a triumph of human intellect, a testament to nearly a decade of unwavering perseverance. He had wrestled with complex mathematics and profound physical concepts, often in intellectual solitude, to construct a new vision of gravity and the cosmos.
This period of focused, almost solitary effort against the backdrop of global conflict highlights the remarkable power of pure thought to transcend even the most challenging external circumstances. In November 1915, amidst the roar of cannons and the suffering of millions, Einstein presented his completed field equations to the Prussian Academy.
The war years, despite the surrounding turmoil, were a period of intense intellectual concentration for Einstein. The relative isolation and the freedom from teaching obligations allowed him to dedicate himself to the final, grueling stages of formulating general relativity. He was largely cut off from direct collaboration with physicists in allied countries, although he maintained some correspondence with neutral colleagues like Hendrik Lorentz in the Netherlands.
This stance further isolated him from some of his German colleagues, but underscored his commitment to humanitarian principles, even amidst widespread conflict. His focus remained resolutely fixed on unraveling the universe's deepest secrets.
This move, orchestrated by Max Planck and Walter Nernst, was intended to provide him with ideal research conditions. However, the outbreak of war shortly after his arrival cast a dark shadow over the continent and inevitably impacted his life, though perhaps less directly than for many others. As a pacifist and an internationalist, Einstein was deeply distressed by the war and the fervent nationalism that swept through Europe, including Germany. Many of his scientific colleagues became caught up in patriotic fervor, contributing to war efforts. Einstein, however, remained aloof from the jingoism, signing an anti-war manifesto, the Manifesto to the Europeans, which called for intellectual cooperation and peace, a stark contrast to the prevailing militaristic mood.
Albert Einstein completed his general theory of relativity in November 1915, a period when Europe was engulfed in the cataclysm of World War I. He had moved to Berlin in 1914 to take up a research professorship at the Prussian Academy of Sciences and a position at the Kaiser Wilhelm Institute for Physics, largely free from teaching duties. The announcement caused, well, a sensation. It was a dramatic vindication of Einstein's revolutionary ideas, a real triumph of theoretical prediction, confirmed by meticulous observation. The eclipse had not only darkened the sun, but had also cast doubt upon the centuries-old reign of Newtonian physics.
The starlight had indeed been bent by the sun's gravity and by an amount consistent with the calculations of general relativity, not Newtonian theory.
After months of careful measurement and analysis of the photographic plates, the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London on November 6, 1919. The observations from both expeditions confirmed Einstein's prediction.
One team traveled to Sobral in northern Brazil and the other to the island of Principe off the coast of West Africa. Their mission was to photograph the star field around the sun during those brief minutes of totality and then compare these photographs with images of the same star field taken at night several months earlier when the sun wasn't in that part of the sky.
The opportunity to put this prediction to the test came with the total solar eclipse of May 29, 1919. Two British expeditions, organized by the Astronomer Royal, Sir Frank Watson Dyson, and led by Sir Arthur Stanley Eddington and Andrew Crommelin, set out to make the crucial observations.
Einstein calculated the precise amount of deflection predicted by his theory, about 1.75 arc-seconds for light just grazing the sun's limb. That's a value roughly twice what you get from a naive Newtonian particle theory of light, if light were affected by gravity at all.
The only opportunity to observe these stars would be during a total solar eclipse, when the moon temporarily blocks the sun's bright disk, allowing the faint light from nearby stars to be photographed.
Measuring this tiny deflection, though, was an incredibly challenging task. The effect would only be observable for stars appearing very close to the sun in the sky, but of course the sun's own brilliance would normally render such stars invisible.
According to Einstein, light from a distant star passing close to a massive object like the sun should have its trajectory deflected by the sun's gravitational field. This would cause the star to appear slightly shifted from its true position.
General relativity made several specific, testable predictions that actually differed from those of Newtonian gravity. One of the most striking and honestly accessible of these predictions was that gravity should bend the path of light.
Albert Einstein's general theory of relativity was, well, a monumental intellectual achievement, a beautifully consistent mathematical framework that offered a whole new understanding of gravity. But like, any scientific theory, it really needed experimental verification to gain widespread acceptance. His journey from an obscure patent clerk to the most famous scientist in the world was, well, complete. The ascendancy that began with the dawning recognition of his 1905 papers had culminated in a reordering of the heavens and the creation of a new cultural icon, forever changing the landscape of science and its place in the popular consciousness.
My rise to global prominence marked a shift in the public perception of scientists. I became the first true scientific superstar, a figure whose pronouncements on a wide range of topics were sought after and reported globally. While I sometimes found the demands of fame burdensome, I largely bore them with grace and a sense of humor.
He became a symbol of humanity's capacity to unravel the deepest secrets of the cosmos, a figure who had, in a sense, peered into the mind of God. His theories, though understood in detail by only a few, represented a profound intellectual adventure, and the public was eager to celebrate its hero.
The public fascination with Einstein was partly due to the abstract and, honestly, mysterious nature of his theories, which really captured the popular imagination. Concepts like curved space-time and the relativity of time seemed to hint at a universe far stranger and more wondrous than anyone had previously conceived.
Yet Einstein understood the unique platform his celebrity afforded him. He realized he could use his influential voice to speak out on issues beyond science that were dear to his heart. Things like pacifism, international cooperation, Zionism, and civil rights.
I became the very embodiment of genius. This sudden ascent to global icon status was, I must say, a complex experience. On one hand, I was gratified by the scientific recognition of my work. On the other, I was often bemused and sometimes overwhelmed by the intense public adulation and media scrutiny that accompanied my newfound fame. I never sought the limelight. I preferred the quiet contemplation of research.
Newspaper headlines around the globe blared sensational news. Revolution in science, new theory of the universe, Newtonian ideas overthrown. The London Times, for instance, famously proclaimed, "Lights all askew in the heavens, men of science more or less agog." Suddenly, the name Einstein was on everyone's lips, and his image with those thoughtful eyes and famously unruly hair became instantly recognizable worldwide.
The confirmation of general relativity by those 1919 solar eclipse expeditions catapulted Albert Einstein from a highly respected physicist within the scientific community to, honestly, an international celebrity of unprecedented fame.
This recognition brought with it a profound sense of duty. I realized that my voice, now amplified by my global celebrity, could be used to champion causes I held dear, to speak out against injustice, and to advocate for a more peaceful and rational world. Thus, the reluctant icon began to embrace his role as a public figure, using his influence to engage with the pressing moral and political issues of his time.
This immense fame, however, came with an undeniable weight. While it opened doors and provided him with an unprecedented platform, it also meant that his every word and action were scrutinized. He could no longer be just a private citizen. He was Albert Einstein, the world's most famous scientist.
There was also a deep appreciation for the narrative of my rise. The patent clerk who, through pure thought, had revolutionized science. In a world still reeling from the devastation of World War I emerged as a symbol of human intellect's power and the enduring quest for knowledge, a beacon of reason and progress.
The public's fascination with Einstein was, really multifaceted. It stemmed partly from the sheer audacity of his ideas, which challenged everyday intuitions about reality and hinted at a cosmos far more mysterious and malleable than previously imagined. He was the man who had, in popular perception, overthrown Newton, redrawn the map of the universe, and unlocked secrets that had eluded humanity for centuries.
I often expressed a bemused detachment towards the intense adulation I received. I was a man who cherished solitude for my work, a quiet thinker who found deep satisfaction in the pursuit of understanding the universe's fundamental laws. The constant demands of public appearances, the endless request for interviews, autographs, and opinions on every conceivable subject, often felt like an intrusion upon my precious time and mental energy. I once quipped that the reporters and photographers followed me around as if I were a Rosicrucian calling up a new ghost. Yet despite my personal preference for a more private life, I handled my newfound status with a characteristic blend of humility, gentle humor, and an awareness of its potential responsibilities.
This sudden, overwhelming celebrity was a phenomenon he had neither sought nor entirely welcomed.
Newspaper headlines across the globe trumpeted my name, attempting to explain my revolutionary concepts of warped space and relative time to a fascinated, if often perplexed, public. My image, with its kind, intelligent eyes and that distinctively untamed shock of hair, rapidly became an instantly recognizable symbol of unparalleled genius. I was no longer just a scientist. I had transformed into a global icon, a figure of immense public curiosity and admiration, unlike any scientist before me.
Following the dramatic confirmation of his general theory of relativity in 1919, Albert Einstein was thrust from the relatively cloistered world of academic physics into the dazzling, often bewildering glare of international public fame.
Yet I remained steadfast in my convictions. I believe it is the duty of intellectuals and public figures to speak truth to power, even when that truth is uncomfortable. My commitment to peace is an integral part of my broader humanitarian worldview, a profound expression of my conscience that is inextricably linked to my scientific quest for universal order and harmony. I feel a moral obligation to use my influence to work towards a better future for all humankind.
His unwavering pacifist stance, however, was not always popular, especially in an era still marked by intense nationalism and geopolitical tensions. He faced criticism from those who viewed his ideas as idealistic or impractical, and sometimes even as unpatriotic.
I firmly believe in the power of education, reason, and international institutions to overcome these challenges. Organizations like the League of Nations, I hoped, could provide a framework for peaceful conflict resolution and collective security. I argued passionately for universal disarmament, believing that the very existence of large military establishments made war more likely. I envisioned a world where disputes were settled by international arbitration, not by force, and where the common interests of humanity transcended narrow nationalistic loyalties.
His voice carried significant moral authority, resonating with many who yearned for a world free from conflict. Einstein's pacifism was not naive. He understood the complexities of international relations and the deep-seated nature of human aggression.
I believe that war is not only morally reprehensible, but also profoundly irrational. It diverts precious resources and human potential away from constructive endeavors. I have lent my name and support to various pacifist organizations and spoken frequently at peace rallies, urging nations to abandon the destructive cycle of arms races and to seek diplomatic solutions to their conflicts.
After the war, as his international fame grew, Einstein became an increasingly outspoken advocate for peace and disarmament. He used his prominent public platform to condemn militarism in all its forms and to call for international cooperation and understanding as the only path to lasting security.
The horrors of the First World War, which I witnessed firsthand during my time in Berlin, only served to strengthen my pacifist beliefs. I was appalled by the senseless slaughter and the nationalistic fervor that had driven nations to war. It was, in my eyes, a catastrophic failure of human reason and morality. War, to me, is a primitive and barbaric solution to international disputes.
Albert Einstein was a lifelong and deeply committed pacifist. His aversion to violence and militarism wasn't something that came about just because of his fame. It was really a conviction that had taken root much earlier in his life, probably influenced by his experiences with the authoritarian German schooling system and his early renunciation of German citizenship to avoid compulsory military service. He became a bridge between cultures, a citizen of the world using the universal language of science and reason to connect with people from all walks of life.
I was greeted as a hero, a sage, a symbol of human potential. The public's fascination with me was immense, and my interactions with renowned scholars or curious onlookers were meticulously documented by the press. While the constant attention could be exhausting, I understood the unique opportunity these travels provided. I could foster goodwill, encourage scientific exchange, and advocate for the causes that mattered most to me.
His presence often drew enormous crowds, and his words were widely reported, allowing him to communicate his vision for a more rational and peaceful world to a global audience far beyond the confines of scientific journals. His voyages also served to solidify his status as a truly global figure.
I spoke about the importance of intellectual freedom, the dangers of excessive nationalism, and the urgent need for international peace. Science, to me, is an inherently international endeavor, a collaborative pursuit of knowledge that could serve as a model for cooperation in other spheres of human activity.
His global perspective reinforced his internationalist outlook and his belief in the shared humanity that transcended national borders and cultural differences. During these international engagements, Einstein consistently used his platform to promote not only scientific understanding but also his deeply held humanitarian and pacifist ideals.
In America, I was struck by the nation's dynamism and technological prowess, but also by its racial segregation and materialism. In Japan, I admired the people's appreciation for beauty and contemplation.
These travels were more than just lecture tours, they were opportunities for Einstein to observe different cultures and societies and to reflect on the state of humanity. He was a keen observer, and his diaries and letters from this period reveal his thoughtful and sometimes critical impressions of the places he visited.
My journeys took me far beyond the academic circles of Europe to places like the United States, Japan, China, Palestine, and South America. I delivered lectures on my theories, engaged with fellow scientists, and met with political leaders, artists, and ordinary citizens. Honestly, everywhere I went, I was left with a profound impression.
With his newfound global celebrity, Albert Einstein became an unofficial ambassador for science and intellectual cooperation, undertaking extensive travels throughout the 1920s and early 1930s. He received invitations from universities, scientific societies, and cultural organizations across the world, all eager to hear from the man who had reshaped our understanding of the universe. For Einstein, supporting a Jewish cultural renaissance and a safe haven was a moral imperative, but one that had to be pursued with justice and a commitment to peace for all inhabitants of the land.
My relationship to the Jewish people has become my strongest human bond, ever since I became fully aware of our precarious situation among the nations of the world.
His involvement with Zionism was thus a nuanced expression of his conscience. He felt a deep responsibility to support his fellow Jews in their aspirations for a secure and dignified existence, yet he also remained critical of any actions or ideologies that he believed contradicted universal ethical principles.
While I supported the idea of a Jewish homeland in Palestine, I consistently emphasized the need for peaceful coexistence and cooperation between Jews and Arabs in the region. I envisioned a binational state where both peoples could live together with equal rights and mutual respect. A vision that was often at odds with the more assertive nationalist currents within the Zionist movement itself.
However, Einstein's Zionism was primarily cultural and humanitarian rather than narrowly political or nationalistic. He was wary of the potential for nationalism to breed intolerance and conflict, a concern that stemmed from his broader pacifist and internationalist views.
I saw the university not just as an academic institution, but as a vital center for Jewish learning and culture, a place where Jewish intellectual traditions could flourish freely. I passionately advocated for its development, lending my prestige to the cause and serving on its board of governors.
His public support for Zionism began in the early 1920s, significantly influenced by figures like Chaim Weizmann, a prominent Zionist leader and chemist who would later become the first president of Israel. Einstein accompanied Weizmann on a fundraising tour of the United States in 1921 to support the establishment of the Hebrew University of Jerusalem.
I recognized the long history of persecution and discrimination faced by Jews and came to believe that a cultural and spiritual homeland could offer a refuge and a center for Jewish identity and intellectual life, fostering a sense of dignity and security.
Albert Einstein's relationship with his Jewish identity and the burgeoning Zionist movement of the early 20th century was complex and deeply personal, evolving throughout his life. Though raised in a secular Jewish family and not religiously observant in a traditional sense, he felt a strong sense of kinship with the Jewish people, particularly as he witnessed the rising tide of anti-Semitism in Europe. His commitment to civil rights was a natural extension of his deeply felt humanism and his belief in the inherent worth of every individual. He saw the fight against racial injustice as part of the larger struggle for a more just and equitable world, a struggle that required constant vigilance and active participation. For Einstein, science and conscience were inextricably linked. The pursuit of truth in the natural world went hand in hand with the pursuit of justice in the human world. His outspokenness on civil rights demonstrated his willingness to confront uncomfortable truths and to use his influence to challenge the status quo in the name of fundamental human decency.
In 1946, I accepted an invitation to Lincoln University in Pennsylvania, a historically black college, where I delivered a powerful address denouncing racism and received an honorary degree. I told the students that the separation of races was not a disease of colored people, but a disease of white people, and that I did not intend to be quiet about it. Such actions were courageous, especially for a prominent public figure in an era when segregation was still legally entrenched in many parts of America.
He lent his support to civil rights organizations, including the NAACP, and publicly associated himself with prominent African-American figures like Paul Robeson and Webb Du Bois. Einstein used his considerable moral authority and public platform to advocate for racial equality. He wrote articles, signed petitions, and delivered speeches condemning segregation and calling for equal rights and opportunities for all citizens.
Upon encountering the pervasive racial segregation and discrimination against African Americans in the United States, I was deeply dismayed. I saw parallels between the treatment of black people in America and the persecution of Jews in Germany, recognizing the same patterns of irrational hatred and systemic injustice. I did not hesitate to speak out against this inequality, famously calling racism a disease of white people. I believed that such prejudice was not only morally wrong, but also a betrayal of America's professed democratic ideals.
Albert Einstein's profound sense of justice and his concern for human dignity extended beyond his pacifism and his support for the Zionist cause. He was also a vocal and consistent opponent of racial discrimination and a champion of civil rights. His experiences as a Jew in Germany, witnessing the insidious growth of anti-Semitism, undoubtedly sensitized him to the suffering caused by prejudice and bigotry in all its forms. He understood that the denial of rights and opportunities to any group based on their race or origin was a fundamental violation of human principles and a detriment to society as a whole. This conviction became particularly evident during his visits to and eventual settlement in the United States. His pronouncements were often met with disbelief or dismissed as alarmist by those who hoped for appeasement or underestimated the Nazis' brutality. However, Einstein remained unwavering in his assessment, his conscience compelling him to speak out against the impending catastrophe he so clearly foresaw. The rise of Hitler to power in Germany in January 1933 confirmed Einstein's worst fears. He was visiting the United States at the time and made the momentous decision never to return to Germany. His property was confiscated by the Nazi regime, his books were burned, and a bounty was reportedly placed on his head. He publicly renounced his German citizenship once again, declaring that he would not live in a country where civil liberty, tolerance, and equality did not exist. His prescient warnings about fascism, born from a deep moral conviction and a clear-eyed analysis of the political situation, tragically proved to be all too accurate.
He saw Nazism not just as a political movement, but as a barbaric regression, a dangerous ideology built on lies, violence, and contempt for human dignity. Einstein understood that the Nazis' virulent anti-Semitism was a central tenet of their ideology and a precursor to wider aggression. He warned that their militaristic ambitions and their philosophy of racial supremacy would inevitably lead to war and unimaginable suffering. He urged the democratic nations of Europe and the world to recognize the danger and to stand firm against Hitler's regime.
Long before many others grasped the full extent of the danger, I began to speak out, using my international platform to issue stark warnings about the gathering darkness that threatened to engulf the continent. My warnings were not abstract. They were rooted in my direct observations and personal experiences. As a prominent Jewish intellectual and an outspoken pacifist, I was a natural target for right-wing extremist groups in Germany. I faced increasingly vitriolic attacks in the nationalist press, and my theories were often denounced as Jewish physics by Nazi sympathizers within the scientific community. These personal assaults only strengthened my resolve to oppose the forces of hatred and intolerance.
As the 1920s gave way to the 1930s, Albert Einstein watched with growing alarm the ominous rise of extremist political movements in Europe, particularly fascism in Italy, and most troublingly for him, Nazism in his native Germany. Possessing a keen political intuition and a deep understanding of the dangerous currents of nationalism and anti-Semitism, he recognized the profound threat these ideologies pose to peace, freedom, and civilization itself. Albert Einstein, the scientist who reshaped our understanding of the cosmos, also dedicated his life to awakening the conscience of humanity, urging us to build a world worthy of our highest aspirations.
In my later years, especially after the advent of the atomic age, my role as a public conscience became even more pronounced. I grappled with the profound moral dilemmas posed by nuclear weapons. a development my own scientific work had indirectly helped to make possible. I tirelessly advocated for nuclear disarmament and world government, believing that humanity's survival depended on transcending narrow nationalisms and embracing a new level of global cooperation.
His writings often emphasize the importance of critical thinking, individual freedom, and a commitment to social justice as essential safeguards against the misuse of power, whether political or technological. He saw education not just as the transmission of knowledge, but as the cultivation of independent thought and moral character.
He was deeply concerned with the ethical implications of scientific progress, particularly as the 20th century unfolded with its new and terrifying technological capacities. He recognized that scientific discoveries could be used for immense good or for catastrophic destruction, and he implored society to cultivate the wisdom and moral maturity to make the right choices.
I often spoke about the cosmic religious feeling that motivated my scientific quest, a profound sense of awe and wonder at the harmony and intelligibility of the universe. This feeling, I suggested, was a common ground between science and true religious sentiment, one that fostered humility and a striving for understanding rather than dogmatic belief.
He frequently wrote essays and articles for popular magazines and newspapers, sharing his thoughts on education, ethics, religion, the meaning of life, and the future of humanity. Einstein believed that science and human values were not separate domains, but were, or at least should be, deeply interconnected. While science could provide powerful tools and knowledge, he argued that it was humanity's moral compass, our sense of responsibility and compassion, that must guide how that knowledge was used.
Beyond his specific interventions on pacifism, Zionism, civil rights, and the fight against fascism, Albert Einstein evolved into a unique public intellectual, a philosopher-scientist whose reflections on a wide range of human concerns resonated deeply with a global audience. His immense scientific achievements gave him a unique platform, but it was his profound humanism, his wisdom, and his ability to articulate complex ideas with clarity and moral force that cemented his role as a guiding voice of conscience for his generation and for generations to come.
The man who had reshaped humanity's understanding of the universe was now a political refugee, stripped of his home and possessions, a prominent target for a regime that despised everything he represented: intellectual honesty, internationalism, and a profound humanism. His exile had begun.
His renunciation of German citizenship for the second time in his life was a powerful symbolic act. It underscored his unwavering opposition to tyranny and his commitment to the ideals of liberty and justice. He and his wife Elsa initially sought refuge in Belgium, staying for a few months at Le Coq-sur-Mer. But even there, the shadow of Nazi Germany loomed large, and concerns for his safety grew.
In March 1933, from aboard a ship returning to Europe, I publicly announced my resignation from the Prussian Academy of Sciences in Berlin before they could expel me. I declared that I could not serve a state that persecuted its Jewish citizens and suppressed intellectual freedom. Remaining associated with any German institution under Nazi rule would be a betrayal of my deepest moral principles and an implicit endorsement of a barbaric regime. My break with Germany was absolute and final, a painful but necessary severing of ties with the land of my birth.
The decision was clear and unequivocal for Einstein. He would not return to Germany.
My own property in Kaput, near Berlin, my beloved summer cottage, was ransacked by Nazi stormtroopers. My scientific works were publicly burned alongside those of other so-called un-German thinkers, and I was vilified in the state-controlled press as a traitor and a purveyor of Jewish physics. The venomous anti-Semitism I had long observed had now become official state policy, wielded with terrifying efficiency.
While still in the United States, reports flooded in of the escalating Nazi atrocities. Jewish citizens were being systematically persecuted, their rights stripped away, their businesses boycotted, and their lives endangered. Academics, artists, and intellectuals who were Jewish or politically opposed to the regime were summarily dismissed from their positions.
The democratic Weimar Republic crumbled, replaced by a totalitarian regime built on racial hatred, militarism, and the suppression of all dissent. He knew instantly that his native land, the country of his birth, was no longer a place he could call home, nor a place where intellectual freedom or even basic human decency could survive.
The year 1933 marked a catastrophic turning point for Germany and a deeply personal one for Albert Einstein. On January 30th, Adolf Hitler was appointed chancellor, and the swift, brutal consolidation of Nazi power began. For Einstein, who was then visiting the California Institute of Technology in Pasadena, this was honestly the horrifying culmination of the dark trends he had been warning against for years.
My later years were marked by scientific isolation, but Princeton became a beacon for minds seeking knowledge.
At the Institute, Einstein worked tirelessly on his theories, even as the scientific world shifted toward quantum mechanics.
I adapted to American life, appreciating its freedoms, though I remained a critic of its flaws, especially racial segregation.
Princeton became his sanctuary, a quiet town, a modest home, and a new intellectual community.
Surrounded by fellow émigré scholars, I was granted the freedom to pursue my quest for a unified field theory away from the chaos of Europe.
As the Nazi threat grew, Einstein found refuge in the United States, accepting a position at the Institute for Advanced Study in Princeton.
The race for the atomic bomb had begun and the stakes could not have been higher.
Physicists like Szilard, Wigner, and Teller realized the urgent need to alert the US government.
We knew what our former colleagues in Germany were capable of, and the thought of Hitler with such a weapon was terrifying.
News of this breakthrough spread quickly among émigré scientists in America, many of whom had fled fascism.
The implications were clear: a bomb of unimaginable power could be built.
In 1938, German scientists split the uranium atom, unleashing the possibility of nuclear fission and a chain reaction. The world would soon feel the consequences.
My pacifism wavered in the face of such peril. I felt compelled to act.
Einstein's signature set in motion a chain of events that would change history.
Roosevelt responded quickly, authorizing the first steps toward atomic research.
The letter, delivered in October 1939, warned of the potential for devastating new weapons and urged government action.
Though not involved in nuclear research, I understood the danger and agreed to sign the letter.
Alarmed by the threat of a Nazi atomic bomb, Leo Szilard sought Einstein's help to warn President Roosevelt.
I was a spectator to a drama I had helped set in motion.
The equation he made famous powered the bomb, but Einstein himself was kept at a distance.
I watched from Princeton as the project advanced in secrecy, my involvement limited to that single letter.
His focus remained on theoretical physics, not bomb design.
My pacifist views and international connections made me a security risk in the eyes of the government.
Despite his pivotal warning, Einstein was excluded from the Manhattan Project. The scientist who revealed the atom's secrets now fought to prevent their destruction.
The burden of knowledge became a lifelong struggle.
The bombings marked a turning point, driving Einstein to campaign against nuclear weapons.
The power we unlocked now threatened humanity itself.
Though not involved in the bomb's creation, Einstein felt a heavy responsibility.
When I heard the news, I was filled with anguish. Had I known the Germans would fail, I would never have intervened.
The atomic bombings of Hiroshima and Nagasaki shocked the world and devastated Einstein. Though the world did not always listen, Einstein's final years were devoted to ensuring that science would serve humanity, not destroy it.
My activism was a response to the terrible power we had unleashed.
Einstein's warnings were stark. Nuclear war would mean the end of civilization.
Only a supranational authority could save humanity from self-destruction.
He advocated for international control of atomic energy and a world government to ensure peace.
Scientists, I believed, had a moral duty to prevent the use of these weapons.
For the rest of his life, Einstein became a leading voice for nuclear disarmament and peace. His work instilled a sense of wonder and a belief in the profound beauty and underlying harmony of the natural world, a legacy that continues to inspire scientists and thinkers to explore the deepest questions of existence with courage and creativity.
Perhaps more profoundly than any specific equation or application, my greatest legacy is the enduring shift I brought to our approach to understanding the universe. I demonstrated that the cosmos, for all its vastness and complexity, is ultimately knowable, governed by elegant and discoverable physical laws. I taught that imagination is a crucial tool in the scientific arsenal, allowing us to leap beyond the confines of the immediately observable.
Einstein's theories of relativity, both special and general, stand as towering monuments of human thought. They did not merely adjust existing frameworks. They courageously tore down and rebuilt our most fundamental concepts of existence. Space was no longer a static, absolute stage, but a dynamic entity, interwoven with time into a flexible four-dimensional fabric called space-time. Time itself lost its universal metronomic beat, becoming relative, its pace dictated by motion and gravity. And gravity, that most familiar of forces, was revealed not as a mysterious pull, but as the very curvature of space-time, shaped by the presence of mass and energy. These were not just new facts, they were a new reality. The practical echoes of Einstein's abstract insights resonate powerfully in our modern technological world. The global positioning system in our smartphones and cars relies critically on the precise calculations of both special and general relativity to function accurately. Without accounting for time dilation, GPS systems would accumulate errors, rendering them useless within minutes. His famous equation, E=mc², unlocked the secrets of nuclear energy, a power source with immense potential for both progress and peril, a duality Einstein himself grappled with. Furthermore, his theories are indispensable for understanding extreme cosmic phenomena, from the enigmatic behavior of black holes to the expansion of the universe since the Big Bang.
My departure marked not an end, but a transition. The intellectual shockwaves I had generated during my lifetime continued to ripple outwards, fundamentally and permanently altering our perception of the cosmos. I left behind a universe utterly reimagined, a testament to the power of a single dedicated human intellect.
Albert Einstein passed away on April 18, 1955, in Princeton, New Jersey. The world mourned the loss of its most recognizable scientific mind. Yet, while the man was gone, his revolutionary ideas were far from finished with their work. His theories, like seeds planted in fertile ground, were only just beginning to fully blossom, their profound implications continuing to unfold across the vast landscape of science and human understanding. His unwavering dedication to this grand vision, even in the face of immense difficulties and growing scientific isolation from mainstream trends, serves as a powerful inspiration. It highlights his relentless curiosity, his refusal to rest on past laurels, and his profound conviction that the universe possesses a deep, underlying coherence. Today, the quest for a theory of everything, aiming to unite all fundamental forces and particles, continues to drive many leading physicists, fueled by the same spirit of inquiry that animated Einstein's final, magnificent intellectual endeavor.
Yet the significance of my pursuit of a unified field theory extends far beyond my personal success or failure in achieving it.
The subtle interplay between gravity and quantum mechanics, which was rapidly developing during these years, presented obstacles that Einstein, with his reservations about quantum theory's probabilistic nature, found particularly hard to reconcile within his geometric approach. His quest, in his lifetime, remained an elusive dream, a beautiful but unrealized vision of ultimate physical simplicity.
Despite years of intense intellectual effort, countless calculations, and exploration of numerous mathematical avenues, I did not achieve my ultimate goal of a complete unified field theory. The challenge proved to be extraordinarily difficult, perhaps even more so than the development of general relativity.
The dream of a unified field theory was, for Einstein, the logical culmination of his life's work. Having successfully unified space and time, and then revealed gravity as a manifestation of space-time geometry, he sought to extend this unification further. He aimed to incorporate electromagnetism, the force governing electricity, magnetism, and light, into the same geometric framework as gravity. His hope was to find a single set of equations, a master theory that could describe all of nature's fundamental forces as different aspects of a single, underlying reality. He envisioned a universe where all physical phenomena could be derived from one coherent set of principles, a testament to cosmic elegance.
This grand quest consumed my formidable intellect, representing the ultimate expression of my lifelong belief in the fundamental unity and simplicity of nature's laws. An unfinished symphony I pursued until my very last days.
In his final decades, spent at the Institute for Advanced Study in Princeton, Albert Einstein remained a titan of thought, his intellectual fires burning brightly even as he aged. While the world largely celebrated his past triumphs, particularly general relativity, his own gaze was fixed firmly on a new, even more ambitious horizon. He dedicated these later years with unwavering, almost solitary determination to one of the most formidable challenges in all of physics, the search for a unified field theory. He understood that scientific progress, untethered from ethical considerations, could lead humanity down a path of self-destruction, a warning that remains powerfully relevant today. Thus, the legacy of Albert Einstein encompasses not only the brilliant scientist who reshaped our understanding of the cosmos, but also the compassionate public intellectual who grappled with humanity's most urgent challenges. He provided a compelling model of an engaged scientist, demonstrating that intellectual pursuits should not be divorced from a concern for the welfare of society. His unwavering commitment to using his influence for the greater good, his courage in speaking truth to power, and his profound empathy for human suffering ensure that his moral legacy endures as powerfully as his scientific breakthroughs, offering timeless guidance in our ongoing quest for a more just and peaceful world.
After the atomic bombs were dropped on Hiroshima and Nagasaki, I was filled with anguish and a sense of profound responsibility. Dedicating my final years to campaigning against nuclear proliferation and advocating for world government to prevent future catastrophes.
Einstein's engagement with public affairs was often characterized by a remarkable prescience. He issued early and forceful warnings against the rising tide of fascism and Nazism in Europe, recognizing the existential threat they posed to freedom and civilization long before many of his contemporaries.
I was a concerned supporter of the Zionist movement, advocating for a Jewish cultural homeland while simultaneously urging for peaceful coexistence with the Arab population. My moral compass was guided by a profound belief in the inherent dignity of every individual.
Throughout his life, particularly after achieving international fame, Einstein consistently championed causes that reflected his deep humanism. He was an ardent pacifist, speaking out tirelessly against war and militarism, advocating for disarmament and international cooperation as the only sensible paths to global security. He courageously opposed racial discrimination, lending his support to the civil rights movement in the United States and denouncing prejudice in all its forms.
I became, in many respects, the conscience of the 20th century, a figure whose wisdom and humanitarian concerns resonated deeply with people across the globe. My life demonstrated that the pursuit of scientific truth could, and indeed should, be accompanied by an unwavering commitment to justice, peace, and the betterment of humanity.
Albert Einstein's monumental legacy is not confined solely to the rarefied realm of theoretical physics. It extends profoundly into the sphere of human ethics and social responsibility. His scientific achievements bestowed upon him an unparalleled global platform, and he did not shy away from using this powerful voice to address the pressing moral and political crises of his tumultuous era. Decades after his passing, Albert Einstein continues to captivate the global imagination, remaining an enduring symbol of genius, curiosity, and the transformative power of human thought. His image is instantly recognizable, his name synonymous with extraordinary intellectual achievement. But why does he persist as such a potent source of inspiration, appealing to people far beyond the scientific community?
Part of the answer lies in the sheer audacity of my ideas, which stretched the boundaries of human understanding and revealed a universe far stranger and more wonderful than previously conceived. I made people look at reality anew, sparking a sense of awe.
Beyond the content of his theories, it is Einstein's approach to thinking and his personal intellectual characteristics that continue to inspire. He embodied a relentless curiosity, a childlike wonder that he nurtured throughout his life, never ceasing to ask fundamental questions.
I famously valued imagination above mere knowledge, recognizing that knowledge is limited, whereas imagination encircles the world.
This emphasis on creative, intuitive thought, combined with rigorous logic, allowed him to make conceptual leaps that eluded others. His perseverance in the face of complex problems, such as his decade-long struggle to formulate general relativity, serves as a testament to the power of sustained intellectual effort and unwavering determination.
Moreover, my personal story resonates deeply. I was not born into academic royalty, nor was I initially recognized as a prodigy in the conventional sense. My journey from a curious boy, sometimes at odds with rigid schooling, to a patent clerk who quietly revolutionized physics, and finally to a global icon, offers a powerful narrative.
It suggests that profound insights can emerge from unexpected places, and that true genius often involves the courage to challenge established dogma and to think independently. This aspect of his life demystifies genius somewhat, showing it to be less about innate magical ability and more about passion, hard work, and the freedom to question.
Ultimately, my legacy as an inspiration lies in my ability to ignite the spark of wonder in others. I encourage people to look at the world with fresh eyes, to question assumptions, and to embrace the joy of discovery.
For students and aspiring scientists, he is a role model who demonstrates the profound satisfaction that comes from understanding the universe. For the wider public, he represents the pinnacle of human intellectual potential and the enduring importance of striving for knowledge. His story reminds us that the quest to understand is a fundamental human endeavor, one that enriches our lives and propels our civilization forward, fueled by that same insatiable curiosity he so brilliantly embodied. Albert Einstein's intellectual journey, from a curious child mesmerized by a compass to the revered sage who pondered the universe's ultimate unity, is a story for all time. It reminds us that wonder is the wellspring of knowledge, that imagination can illuminate paths unseen, and that the pursuit of understanding is one of humanity's noblest callings. His theories continue to power our technologies and guide our explorations, but perhaps his most lasting gift is the enduring inspiration to question, to dream, and to strive to see a little further into the magnificent mystery that surrounds us. His mind, indeed, continues to encircle our world.
When we speak of the mind that shaped the universe, it is crucial to understand its meaning. I did not physically alter the stars or the laws of nature. Rather, I profoundly and irrevocably shaped humanity's perception and comprehension of the universe. I gave us new concepts, new language, and new tools to describe reality, from the smallest quantum interactions to the grandest cosmic scales. I taught us to see connections where none were previously apparent and to question what was once deemed unshakable. In this sense, I truly did sculpt our understanding of the world we inhabit.
His work stands as a powerful affirmation that the universe operates according to elegant and consistent laws, and that the human mind, in its relentless quest for understanding, is capable of grasping these deep truths. This belief in the power of human intellect remains a cornerstone of scientific endeavor.
At its core, my enduring message is one of profound optimism about the human capacity to comprehend the universe. I believed, with an almost religious fervor, in the underlying order and intelligibility of the cosmos. I showed that even its most enigmatic aspects could yield their secrets to persistent inquiry, guided by reason and imagination.
The legacy of Albert Einstein is not a static monument, confined to the pages of history books or the archives of scientific journals. Instead, it is a living, breathing force that continues to shape our world in countless ways, its echoes reverberating through science, technology, philosophy, and popular culture. His insights have become so deeply interwoven into the fabric of our understanding that it is difficult to imagine modern physics, or indeed our modern worldview, without his monumental contributions. He provided us with a new cosmic lens, and through it, we continue to explore and interpret the universe with ever-increasing clarity